Yeah, we're looking at separable differential equations, one of my favorite topics. So we've solved differential equations like this before. Essentially, you've got the derivative of the function equals x squared. So what we should get is that y is the integral of x squared. That's sort of how derivatives work. They're the opposites of integrals. So y should be x cubed over 3 plus c. C is some real number. But what are we actually doing when we do this? Well, sort of we're integrating both sides with respect to x. So you can think of a middle step here, the y dx with respect to x over here, and then this is just the same thing, x squared with respect to x. We have integrated both sides. Now, sort of, the y dx and then dx, you can think of the integral and then the derivative as like cancelling out each other, and you're left with y. But one other way to think about this is doing another middle step here. So we could think of this one as like the dx's cancel off, and you're integrating 1 with respect to y. What's the integral of 1? Well, it's y. So that's sort of how that works if you step out what the notation actually means. Now that seems needlessly complicated for a normal equation like this, but it's really useful when we solve differential equations like this. dy dx equals y. So the reason we call these separable differential equations is we like to separate it out. So y's are all on the left and x's are all on the right. We can do this by dividing both sides by y. So 1 over y, dy dx, equals, and you're going to get y over y here, which is just 1. So this is divide by y to both sides. And then we can just integrate both sides with respect to x. And what do we get? Well, over on the left-hand side, this just becomes the integral of 1 over y with respect to y. And this is still the integral of 1 with respect to x. So we're going to get a log of y here. And then this is x plus some constant c. Now, how do we deal with this? Well, we can raise e to the power of both sides. So we can just do e to the power of log of y is e to the x plus c. So this will leave us with the absolute value of y is e to the x plus c. And then we can get rid of the absolute value signs. It's going to be a little bit weird, but y is plus or minus e to the x plus c. And then you can sort of split this x plus c into 2 bits. Using your index laws, this is plus or minus e to the x times e to the c. And I'm just going to move the e to the c to the front. So plus or minus e to the c times e to the x. That's what y equals. And then we bundle this entire thing up into a new constant, which we usually call a. Y is a e to the x. So a there is plus or minus e to the c. Usually you can do this in less steps once you are familiar with the patterns and you know what you're doing. But that's really the full process for solving dy dx equals y. Now, with this equation, we can sort of think about, do I know a function f of x that has its own derivative equaling the same thing? And yes, that function would be e to the x. And then that satisfies that the derivative equals itself. But similarly, if we look at f of x equals e to the x, yes, the derivative does equal the same thing. But in fact, any multiple will work. So f of x is 7e to the x. We should find that the derivative there is 7e to the x. So yes, it matches as well. So in general, it looks like ae to the x. So you still get a constant of integration, it's just times, which is a little bit unusual. Okay. Next, dy dx is xy. So we need to separate this. So we need to go 1 over y dy dx. And we'll be left with x over here. And this plays out almost exactly the same. So I'm going to get the integral of 1 over y dy dx dx is the integral of x dx. So this is the integral of 1 over y dy is the integral of x with respect to x. And so that leaves you with just a log of y again on the left-hand side equals x squared over 2 plus c. C is in r. And then you can raise e to the power of both sides. So mod y is e to the x squared over 2 plus c. You can go y is plus or minus e to the x squared over 2 plus c. And then you can split it out. So you can go plus or minus e to the c times e to the x squared over 2. And so we call that thing a e to the x squared over 2. So a is plus or minus e to the c. Done. Okay, this one's a little bit messier, but we can still separate it. So we can multiply by e to the y on both sides. E to the y dx is equal to 3x. Sometimes this is a little bit of dodgy notation, but I like to sort of think of it like this. So like you're timesing by dx on both sides. So you'd be left with dy. And if you times by dx on both sides, you get a dx over here. You just sort of have to whack an integral in front of it. So anyway, you get e to the y here, and you get 3x squared over 2 plus c. So if you want, you could log both sides. So y is log of 3x squared over 2 plus c. C is in R. You don't need an absolute value on that log sign because we didn't integrate to get up to it. There we go. Okay, so in general, if you're looking at something like dy dx equals two functions times together, you can just go 1 over g of y, dy dx equals f of x, and then you can sort of integrate both sides to solve that, and it's a really nice process. If you see something like this, these are generally a lot harder to solve, which you wouldn't think that having a times versus a plus would make so much difference, but it is quite a bit harder to solve this bottom one than the top one. We like timesing with differential equations.